Welcome to this session on research methods, and in this session we're going to be looking at significance levels, sample size and effect size. This needs to be seen in the context of the increasing volume of research in the medical community, which often leads to contradictory findings and conclusions. Although the differences observed may represent real differences in the studies, they could also be due to sampling variability, as all studies are conducted on limited numbers of people. When planning a study, reporting differences among groups of patients or describing some variable in a single group, sample size is important to consider because it allows the researchers to control for the precision of their study. Equally important, when you're reading a paper, you should understand sample size because such understanding is important to understanding the relevance of findings for a particular group of patients. So in this session, we're going to look at a few issues. We're going to look at significance levels and power, sample size, effect size, and bias. Power calculations and effect size are important in designing research studies to determine if an effect is real or due to chance. Power analysis gives power to a specific effect size. For example, a researcher might report, if the treatment increases the recovery rate by 20 percentage points, the study will have a power of 80% to yield a significant effect. So we're going to look at what that means in a little bit more detail. Significance level and power are two important concepts. You will often see reference to one or both of them in research papers. They are closely related concepts, but they can also cause confusion. So let's just look at them both. Significance level is usually set at a particular level, in this case p less than 0.05. What does that figure represent? That figure would mean there is a less than 5% chance risk of concluding that there is a difference, when actually in the real world there is no actual difference. Conversely, there is a more than 95% chance of saying that there really is an effect, and there really is an effect in the world. So another way of thinking about that is, if we were looking to see whether a drug works or not, for example, we've done a study and we want to be more than 95% sure that the study that we've done, which indicates that that the drug works, we'd want to be more than 95% sure that that is the case, and that's what significant level refers to. It refers to our ability to generalize from a particular study to the general population. Power, on the other hand, refers to the probability that a study will detect an effect when there is an effect there to be detected. So we want to be able to show that if there is an effect, that we will have sufficient power to detect that difference. Conversely, there is a 20% probability that we will miss that effect. So power is the probability that a test of significance up here will pick up on an effect that is present. So why are the levels different? We wouldn't want to conclude that a drug works when in reality it doesn't work. That's why we set this level of 95% for significance level. On the other hand, it's not quite so serious to miss an effect if there is an effect there. So that's why power is usually set lower. And it's also related to considerations of sample size as well. So we'll look at that later. Let's just look at the relationship between research findings and the real world again. So over here we have our research findings drawn from a particular sample, and up here we have the real world. So we've done our study, and our study, for example, supports the hypothesis that a drug is effective. However, if in the real world the drug is not effective, we would be making a type 1 error. If, on the other hand, we've done our research study and our results don't support the hypothesis, but actually there is an effect in the real world, that would be an example of a type 2 error. Before we leave the topic of significance levels, they are also often expressed in terms of type 1 and type 2 errors. So let's just look at these for a minute. A type 1 error is also known as a false positive. The study showed an effect which in reality does not exist. In other words, we say that the drug works in the real world, but it doesn't. A false negative is when we miss an effect. So we say that the drug didn't work, but actually it does work. So the probability of making a type 1 error is alpha, which is the level of significance you set for your hypothesis test. An alpha of 0.05 indicates that you're willing to accept a 5% chance that you are wrong when you reject the null hypothesis. If we do not reject the null hypothesis when in fact there is a difference, then this is known as a type 2 error. In reality, researchers want both type 1 and type 2 errors to be small. In terms of significance and power, this means that we want to set a small significance level, as we saw, for instance, close to 0.05, and a large power close to 1. Let's look at an example of power analysis. And to begin with, we start with our research hypothesis. So we hypothesize that 40-year-old men who drink more than 3 cups of coffee per day will score more highly on the Cornell Medical Index than men who do not drink coffee. For the study to have a power of 80%, what sample size is needed? First of all, we need to look at the range of the scale, and the Cornell Medical Index ranges from 0 to 195, where a higher score equals worse health. And we know from previous research that scores on the CMI increase by about 3.5 points for every decade in life. So it is decided that an increase caused by drinking coffee, which was equivalent to about 10 years of age, would be enough to warrant concern. So you can see, in order for us to conduct power analysis, we have to have some idea of the effect that we're looking for. So we're interested in an increase approximately equivalent to 1 decade caused by drinking coffee. And thinking back to our earlier presentation on statistics, inferential statistics, the relevant test would be a one-sided t-test with 2 independent groups, one drinking coffee, one not drinking coffee. We know that the average score for men in their 40s on the CMI is 8, and that the standard deviation is 7. We've decided that an increase of 3.5 will be sufficient to concern us. So what we can do is use a calculator, enter these figures, and it will tell us how many people we would need to evaluate in each group in order to have a power of 80%. That is concluding that there is an effect in the population when there really is an effect in the population, and a 20% chance of missing that effect. So if we put these numbers into the calculator down here, you can see population 1, population 2 showing a hypothesized increase from 8 to 11.5. It will tell us that we need 51 people in each group in order for there to be a power level of 80%. So that's an indication of how we determine power analysis in relation to a particular study that we're conducting. Here's a review question based on the concepts that we've just been discussing. If the significance level of a study is set at p less than 0.05, which of the following is correct? Is it A, B, C, or D? Let's just have a look at those four options. So the question asked, if the significance level of a study is set at p less than 0.05, which of the following is correct? And the correct answer is B. There's a less than 5% probability of concluding that a difference exists when there is no actual difference in the real world. Statement A is incorrect because it says greater than 95% probability of concluding that there is a difference when there is no actual difference, but actually there is a difference. So there's a greater than 90%, 5% chance of being correct in generalizing from our sample to the population. So that's why that statement is incorrect and why this statement is correct. Another review question. If the power of a study is set to 80%, the probability that the study will miss an effect is which? Is it 80%, 20%, 50%, or 8%? So what does power relate to? The correct answer is B. In other words, there's a 20% chance that our study will miss an effect in the real world. Another question that often concerns people is how many people should I interview if I'm going to do a survey? Here the crucial thing is what is the exact research question that you are asking. Only with this information are you able to answer the question, how many people should I interview? For example, in this example here shown on the slide, suppose that in a survey of the general population, the estimated proportion of respondents in last year using a pharmaceutical drug was 17%. I want to know how true is this likely to be of the population. So the key factors that we have are the rate that we found in the sample, which was 17%. What error are we willing to accept? And in this case, I put in the parameters of plus or minus 3%. So in the general population, I'm willing to have a deviation of plus or minus 3%, and I wish to be 95% confident that truly in the population, the rate does lie between 14 and 20%. Of course, it could lie out with that because it's a 95% confidence interval, as we've already discussed. So I would enter these parameters into an online calculator such as the one shown here, and it would tell me that I would need to interview a minimum sample of 599 people. So if I was to go ahead and interview 599 people, and what I would then be able to conclude was from a sample of 999 people, a survey sample rate of 17% represents a true population rate of somewhere between 14 to 20%. Here the question is slightly different. I want to know if there is a significant difference between those who have used a pharmaceutical drug and those who have used an illicit drug. So suppose that an estimated proportion of respondents in the last year using a pharmaceutical drug was 17% and it was 11% for an illicit drug. So these are the same people asked two different questions. What sample size would I need to be able to detect this difference? So the first thing I need to think of is what is the confidence interval that I would like around this difference. So if I want to be 95% confident, then I would need to choose a particular sample. And secondly, what power would I need? In other words, if there is an effect, how many people would I need to find that effect? So again, we can put these parameters into a sample size calculator, and we find that if we select 441 people and determine that 17% and 11% have the factor of interest, then we would have an 80% power to declare that the proportions are significant difference at the 95% confidence interval. So there are a few things to think about in relation to sample size. Number one, what degree of confidence is needed? Suppose that in a random sample of 100 people, the number of times people report feeling unwell per year is 40 with a standard deviation of 10. For a given sample size, if you want to know the true population mean, what you need to do is make the confidence interval wider. So for example, here we can see that if we have a 95% confidence interval, we can see that the 95% confidence interval is 36.8 to 43.2. So we can be 95% sure that it lies between those values. If we want to be more sure, for example, 99%, then the confidence interval will be wider. It will be 32 to 47. So we can be 99% sure that it will lie between these two values. Question number 2 relates to how many data points are you going to need? And again, this relates to confidence intervals. So with larger samples, confidence intervals are narrower. If we have 100 people, with a mean of 40 and a standard deviation of 10, our confidence interval will be 38 to 42. If we increase the sample size, we can see that the confidence interval goes down to 39 to 41. In other words, with a larger sample, the confidence interval is narrower. And the third factor to consider is how scattered are the data. If the data are more scattered, the confidence interval will be wider. So for example, with 100 people, if we have a mean of 40 and a standard deviation of 10, the confidence interval will be 38 to 42. If the mean is 40, but the standard deviation is much larger at 40, then our confidence interval will always also be wider, and it will now be 32 to 47 compared to 38 to 42. Bearing in mind what we just talked about, let's have a review question. With a larger sample compared to a smaller sample, and with a given mean and standard deviation, will the confidence intervals be narrower, wider, the same, or cannot say? So those are the 4 options to think about. So we can see that with a larger sample size compared to a smaller sample size, for a given mean and standard deviation, the confidence interval will be narrower. So in thinking about going about choosing a sample survey, what are the things that we need to think about? First of all, you need to determine your population of interest. For example, if I'm interested in the efficacy of the drug melatonin for patients, am I interested in all patients receiving the drug, all patients aged 18 to 30, or all patients aged 18 to 30 living in North Staffordshire? We need to establish our baseline population. We need to estimate how many individuals are in that population. And then we need to determine how confident we are that our results are representative and be accurate. If we're doing a survey, we also need to think how many surveys will we need to send out based on how many people might respond. For example, if we only expect 50% of people to respond, then we would need to double the number of surveys that we need to send out. So there are many factors to be considered when choosing a survey sample framework. There's some other factors we need to think about in relation to sample size. Firstly, there's the nature of the analysis to be performed. Secondly, is the desired precision of the estimates one wishes to achieve in terms of confidence intervals. Thirdly, is the kind and number of comparisons that will be made. The more breakdowns there are in your data analysis, for example, by age, gender, the larger the sample needed. And finally, how heterogeneous or dissimilar is the population being sampled? We've seen before that if the population has a large standard deviation, we will need a larger sample size to reduce confidence intervals. Let's look at another concept that you will sometimes see mentioned in studies, and that is effect size. So a small effect size is one in which there is an effect, something is really happening, but you can only see this through careful study. A large effect size is an effect size which is big enough and consistent enough that you may be able to see it with the naked eye. For example, by looking at a room full of people, you'll probably be able to tell that on average that men are taller than women. That is what's meant by an effect size that can be seen with a naked eye. So an example perhaps of a small effect size is something that I looked at a few years ago, which was the effect of cannabis on development of schizophrenia. It's not something that you can detect with the naked eye. It's something that needs careful study. And if there is an effect, the effect size may be relatively small, and it may also depend on other factors. Effect sizes can also be interpreted in terms of the percentage of non-overlap of the treated group scores with those of an untreated group. So for example, if we look here and we see, for example, on the left the treated group and on the right the untreated group, say for example looking at blood pressure, and we see that the treated group has lower blood pressure. Where this degree of overlap between the two distributions is very low, then we will have a high effect size as shown over here. So for example, an effect size of 2 means that the percentage of non-overlap is very high, 80%. Where the effect size is small, for example, down here, the percentage of non-overlap is very low, or in other words, the percentage of overlap is very high. So for example, in this example here, you can see that there's quite a lot of overlap between the two distributions. So the effect size is just another way of conceptualizing the difference between two groups in terms of some outcome measure. This slide shows the calculation of effect size. You can see here that the basic formula has the mean for one group minus the mean for another group divided by the standard deviation. And you'll notice that sample size doesn't appear anywhere in this calculation, so it's not dependent on sample size. And we can see that down here, for example, where we have a mean of 20 in one group and a mean of 24 in another group, and a standard deviation of 4.53, we have an effect size of 0.88, which is quite a large effect size. So it's quite a nice way of thinking about the difference between two groups in terms of whether there's a large effect size or not. So one of the things that people often ask is, how should I go about calculating sample size or confidence intervals? And as we've seen throughout this presentation, it very much depends on the type of comparison being made. And here I've just put in some links to some places on the internet where you can find different ways of doing these calculations. But ultimately it goes back to the kind of question that you're asking. Now we're going to look briefly at the issue of sample size in qualitative studies. And the first point to note is that the same considerations do not apply for qualitative studies, as these are not based on statistical consideration. The validity, meaningfulness, and insights generated from qualitative inquiry has more to do with the information richness of the cases selected and the analytic capabilities of the researcher than with sample size. So there are no definite rules to be followed in qualitative studies. It will depend on what you want to know, the purpose of the inquiry, and so on. With fixed resources, you can choose to study one specific phenomena in depth with a smaller sample or a bigger sample size when seeking breadth. And I'll just talk briefly about one recent research project at Keele, which was looking at stakeholders involved in the treatment of familial hypercholesterolemia, or FH. So this was a study where we were interested in what both patients and doctors' views were on the barriers and facilitators to treatment with different drugs for this condition. So what the student decided to do was a semi-structured questionnaire. It was a qualitative study with a small group of patients and a small group of doctors. And the type of questions that were asked, I'll give you a couple of examples. One question was for patients, please describe the treatment journey you have had before receiving treatments. So it's an open-ended question to which the patient can respond, and the researcher had various prompts such as screening, diagnosis, feelings, effective life, etc. Another open-ended question was, what were your experiences through this journey, both good and bad? And this time the prompts were timing of diagnosis, provision of medicine, efficacy of medicine, family and friends. And in this project, only a small number of patients were interviewed, but a lot of information was gained from these few patients. So the issue of sampling size wasn't of primary importance. What was more important was when the researcher felt that the themes had been, all the necessary themes had been explored and no new information was being gained. So that just shows you some of the information that you need to think about in relation to quality. Instead of just interviewing people one at a time, we might want to have an interview with a group of people to explore their mutual experiences of a phenomena. This is an example taken from the International Journal of Pharmacy Practice, and it was looking at physicians and nurses' experiences of multidisciplinary collaboration with pharmacists. So what the researchers did was conduct focus group, that is interviews with a mixture of physicians and nurses. They were recruited from 3 different nursing homes which had previously identified and resolved drug-related problems. And physicians, 3 men and 1 woman, and a purposeful sample of 6 nurses were invited to take part in professional focus group interviews. So quite a small sample. Purposive sampling is a type of non-probability sampling technique, in other words, not statistical. And this really relies on the judgment of the researcher to elicit interesting information. So again, the key point here is that we're not using statistics to inform the sample size. We're using questions about relating to the meaning and interpretation of the data. Another point to bear in mind is that just because we have an adequate sample does not ensure that the data will be representative or accurate. So errors, non-sampling errors can arise from a number of sources, a couple of which are shown here. For example, it could be that the questions are not very well phrased and people don't understand the questions, or they misinterpret them. And it could be something about the social desirability of the response, that people feel that they have to give a particular answer. And we could imagine that in the Keele project of FH, that these kind of errors could have fed into the results. So that's just something to think about when we're either conducting a study or interpreting data. Epidemiological studies are also subject to bias as well. In another session, I mentioned this paper which looked at the relationship between getting hypnotic drugs and mortality. So the exposure was getting prescriptions of these drugs. The outcome was mortality, and we did consider a number of factors that could confound this relationship. However, there is scope for measurement error at all stages of this process, And there are also issues to do with the cases that we follow up. Are they necessarily representative? So there's scope for selection bias, which needs to be carefully looked at in epidemiological studies. We mentioned the issue of people giving socially appropriate answers, or the answers that they think interviewers want to hear, and that's illustrated in this study called Interviewer Bias Effects on Self-Reported Drug Use. So quite often this issue is not really investigated in very much depth, but in this study they did set out to look at it, and they had two types of interviewers: people who were, quote, straight interviewers wearing suits and ties, and people who were, quote, junkie interviewers who were more casually dressed. They were ex-drug users. And what the study found was that people's answers were different to the two types of interviewers. So the answers depended on the motivational state of the respondents. It's not that they're not telling the truth, it's just that their motivation is different in different circumstances. So again, it's just another type of bias to be aware of, and this is a reference which explores this in more depth. And finally, just a summary of what we've covered in this session. So we've looked at significance levels, we've looked at power calculations, we've looked at effect sizes, we've looked at different sources of error and bias. If you'd like further information on these topics, I've listed a couple of websites that you can look at which contain more information.